Hello and welcome back.
Hi everybody. What we're going to do is we're going to split lesson 2.7 into two separate days just because it's a lot of stuff. So this is the first half of that stuff. So you'll see your learning targets are broken up into 2 days. Thank you for the 2 days. All right, so for the rest of the chapter, we're going to be dealing with rational functions. What's a rational function, Mr. Leckie?
It's a function that makes a fraction out of polynomials.
Out of polynomials. So f of x and g of x are polynomials.
And g of x cannot be...
What? It's on the bottom.
0.
0.
No dividing by 0. Bad things happen to life.
Bad things.
Black holes. That kind of end of the world as we know it.
Okay, so now we're going to have to review a little bit of our end behavior rules. You remember our end behavior rules?
End behavior. That would be the limit as x goes to infinity.
Yep.
And the limit as x goes to negative infinity.
Okie dokie. I was ready to do the whole... Never mind.
I don't want to go as x goes to anywhere.
Okay.
All right, so when x goes to infinity on this picture, that curve is going up, which is positive infinity in the y world. And as limit as x goes to negative infinity, if you notice, it's not going up or down. It's actually starting to flatten out and level off, and it's going closer and closer to the y value of 1.
Alrighty. We still have students, now that it is October, not writing this notation correctly.
Tomorrow's Halloween.
So
I don't know what time you're watching the video, but hey.
It is Halloween tomorrow. Okay, so you've got to get this limit notation down. Please come see us if you're struggling with that. All right, so for all rational functions, if it is a rational function, if the end behavior is a numeric value, as in a number,
like the 1 in the example above,
like the 1, then the end behavior will be the same as you go to plus and minus infinity.
So that's not a rational function that's graphed on the board. We can still talk about its end behavior, but that would not be a rational function because it has different end behaviors.
So let's look at some rational functions. We have 3 examples for you, and all rationals can fit into any of these 3 categories. So let's look at letter A. What do we notice?
We have a very strange graph.
Isn't it cool?
What do you notice?
I notice that the end behavior as x goes to negative infinity is flattening, and as it's going to positive infinity is flattening.
They look like they're both getting closer to 0.
They are, and they're both going to the same direction. If you want to be really fancy, you could do that. Ooh,
you could. As long as it's a rational function, I suppose we'll let you get away with it.
Yes.
And the limit's going to go to 0 because that's where the y values are approaching on both ends of the number line. We don't care what happens in the middle.
Safe.
Safe.
Okay, let's look at letter B.
Well, we also have a rational function, and this one is leveling off at negative 4 on the left side. It looks like negative 4 on the right side. So we have the limit as x approaches positive or negative infinity. G of x this time is actually going to go to negative 4. And both of these have numeric values.
That's why you can write the plus or minus.
You notice they're going to the same number in both directions.
Okay.
The next one doesn't work out so well.
Not so much.
Because it's not going to a number. This function is actually going up and down for infinity. So we have to break it up first of all. And as x goes to infinity, we're going to infinity for h of x.
Yep.
And this is not new. You have done this before given pictures. Our goal today is to try to do this without the picture and to use the end behavior, along with a few other things, to generate that picture. We will be generating the pictures next class.
We will.
Not this one. Today we're just going to make sure you can do as much as possible, just finding as much information about the function and hopefully generate these pictures without a calculator. It can be done. It's amazing.
Okay, so now that we have our end behaviors, instead of looking at the picture, let's look at the functions, okay? So those are those same end behaviors that are copied across, okay? We just needed another screen. Yours is probably on the same paper. And the end behavior uses only which term?
Just the leading coefficient.
Just the leading coefficient.
And the highest power.
And the highest power, the degree. So it would make sense that if a rational function is built of polynomials, and for a polynomial you look at the biggest thing, if you will, on the top, and the biggest thing on the bottom, then for the rational, could we just look at those same 2 biggest pieces?
Yep, just make a ratio out of them or a fraction. Just look at x over x squared. We call this the end behavior model.
Well, x over x squared, doesn't that just reduce to
1 over x? Yep.
Hey, that was a parent function.
And as x goes to infinity of 1 over x, do you notice that the y values will go to 0? Now, although they go to 0 from above is 0 and below 0, they both go to 0.
Yep.
And we have the same end behavior, the same infinite limit on both sides.
I love it when math works out like that.
Amazing. So what would that end behavior model be of letter B here?
Letter B. So we got to look at the biggest thing on the top.
4x cubed. So
or the
far, there's been
first
only one
term,
thing
if
on
you
the
will.
top.
And the first thing on the bottom.
Negative x cubed.
So this end behavior, if you will, I like to abbreviate that, would be 4x cubed over negative x cubed.
That's going to simplify to negative 4.
It sure is. Looky, looky.
That is where our end behavior went.
Okay. So you mean we don't really need the picture?
Nah, we could actually do this with an end behavior model. In the first two examples,
so
we had x on the
cool.
bottom, or we had more x's on the bottom.
Right?
Okay, and then we ended up going to 0. And
Yes, we did.
And the other one, we had x cubes, top and bottom, so they all canceled, and we ended up with a ratio of negative, 4 over negative 1.
Right.
Basically, the idea here is how fast these fractions grow.
Okay.
If the bottom grows faster, the whole thing goes to 0. If they grow at the same rate,
Then it
there's a
goes to
ratio.
some value. Okay.
But
Let
now
us
this last
see.
one, we have an x squared over 2x for end behavior. So the top actually is growing faster than the bottom. And this reduces to x over 2. And as x gets really large, that fraction gets really large in the positive direction. And as x gets very negative in the negative direction, it will go to negative infinity.
Could we think of this as 1/2 x?
Sure, we could.
Isn't that like a positive odd?
Yeah, your little muscle beach thing.
My little muscle
It's a line that goes.
It's a line. It's a line. I don't have very many muscles. I'm a line. Okay, so it's the same stuff that we were doing before. Okay, so this would be x is bigger on the top. Okay, so we've got 3 scenarios there.
Yep.
Where are the extra x's left over? Okay, so, Mr. Lucky,
All right, let's see if we can
Calculus.
talk about maybe why this works. We want to talk about just how things grow faster on the top or the bottom.
Okay.
That's really what our goal is. But let me just show you how this kind of works. We got a couple of ways we can think about this. First off, consider h of x is 1 over x. So if I had the graph of 1 over x, as x goes to infinity, going this way, our y values are getting closer and closer to what value?
to 0.
0. They don't actually hit it. That's just terrible board work here. So as x goes to infinity, h of x approaches 0.
It does.
In both directions, actually,
In both
but we'll talk
directions.
about just the positive direction for now.
Okay,
Okay, so let's rewrite this. Now, there's a lot of ways to rewrite this.
there are.
We're going to go ahead and try this with some long division.
Sounds
Is that
good?
okay with you?
That sounds good.
And I'm just going to grab a new page just so you can kind of see that we had 4x cubed divided
did.
by 27 minus x cubed. So that's really
Remember
negative
that.
x cubed plus 0x squared plus 27.
27.
But I'm going to kind of cheat a little bit because I know it's going to work. But I'm just going to leave out all those extra terms for a moment. Is that okay?
That's fine.
All right, so when we divide these things, we get we got to use a negative 4,
X.
and that's it.
Nothing, yeah.
Right?
That's it.
So we get negative 4 times negative x cubed is positive 4x cubed. And then we have a plus 0 up here. We really have a 0x squared, a 0x, and a 0.
We do.
But we don't have any of those x squareds or x terms over here, so we can get away with it. And this is minus, what is that, 108?
Yeah.
Hopefully that's right. 25 times 4 is 100, and 2 times 4 is... So we're going to subtract, and we get a remainder of 108. Is that okay?
That's great.
So we have this 4x cubed divided by 27 minus x cubed is really negative 4 plus a remainder of 108 over 27 minus x cubed.
Correct. That was just long division from last chapter. It looks a little funny, but it was long division.
And the idea was, in the last example, we said 1 over x goes to 0 as x goes to infinity because the numerator was constant. It was a 1.
Right.
And the denominator is going to get incredibly large. So as a fraction, it goes to 0.
So 1 divided by something really, really big is really, really small, close to 0.
Yeah, absolutely.
Okay.
So this idea works the same. As x goes to infinity, remember, we're worried about what the end behavior of this model is, but it's equal to negative 4 plus a remainder. But
Right.
what happens to the remainder as x goes to infinity?
Well, it's 108, but it's divided by something that's getting bigger and bigger and bigger.
So
So it's really going to 0.
this fraction, the remainder, is going to go to 0.
If the remainder is going to 0, doesn't the polynomial or the rational function go to negative 4?
So that means this whole thing, as a function, is going to approach negative 4 as x goes to infinity.
Okay.
All right, so there are other ways to do this, and we could go through those processes later in class if we want to. We could divide everything by x cubed and see what happens. We may have some examples like that in class. But for now, it's just a way to just kind of convince you that all the things we were doing before, especially all this long division stuff,
Right.
has a purpose.
It
one.
does.
And 2, to show you that as x goes to infinity, every time you divide two polynomials, the remainder will always have a higher power in the denominator. Otherwise, you weren't done dividing.
Right.
So the remainder will always go to 0, and this is the end behavior of your function. The quotient is.
Great.
And if that's a number, that number is going to be a horizontal asymptote in just a moment.
Safe.
Okay. All right.
Okay. So here's what we're going to do. We're going
I
to
think we
take.
skipped. What did this say?
Well, what we're going to be doing is we're going to be putting all this together with what we already know about domain, vertical asymptotes, holes, things that we knew from chapter 1. Okay. So we've had some time for that to marinate, I like to call it, and now we're going to actually apply it
Let's
to
do it.
rational functions. Okay. So they've given us an equation, and the first thing we need to do is find the end behavior. So what we can do is look at the end behavior model, which would be 2x squared.
End behavior model. You can call it EBM if you want to. Which is
2x
squared
over 2x squared.
which is equal to.
1.
So,
So-
as x goes to infinity,
Why don't we write it with limit notation?
I'm stuck in algebra 2 mode. So the limit as x goes to plus or minus infinity, we'll just talk
Right.
about infinity for the moment, is h of x is equal to
1.
1. It's that, there's no x in this. X could go off into the woods for all I care. That's 1's going to stay as a 1.
It is.
Doesn't matter where it goes. Now, if that's a number, on our graph, that was where the graph was approaching, yes?
Right. It was.
We call that a what?
A horizontal asymptote.
So if this is an actual number, then we have a horizontal asymptote
At y equals 1.
at y equals 1. Make sure it's written as an equation of a horizontal line,
Please.
y equals 1. And if you have a horizontal one, you can't have one of these, and we'll talk about how to find those in a minute.
Okay.
Okay. All right, so now we have the horizontal asymptote.
We do. We are ready to look at vertical asymptotes. Well, for the rest of this problem, and remember, later on, you're going to be dealing with more than just these two pieces of information. All we can tell you is factor, 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 factor.
Everything factor.
2x squared.
Every day of life, I find another person who can't factor.
All right, so we're going to take a 2 out of the top.
We're going to...
We're going to have x squared minus 9 left. So how about x plus 3 and x minus 3? I was ready.
I know.
It's okay.
This is x plus 3.
And x minus
3.
And then in the denominator, we have our 2x squared minus 11x plus 15. That's going to be 2x minus 5. And x, I believe it's minus 3.
So crappy. Minus 3. All right, so this is mostly readable. All right.
Okay, so domain.
Domain are the numbers we can use in this whole fraction.
Right, anything that makes sense. And
but we
because it's a
can't
fraction,
divide by 0.
we can't divide by 0. So what value is going to make us divide by 0?
Well, there's a 3 that would
Yep.
make this factor 0, and there's a 5 halves that would make that factor 0. So that was the
Correct.
point. That was the reason we factored the bottom.
Exactly. So if we look at that, our domain would be everything except for 5 halves and 3. Which means that 5 halves and 3 must be something else.
There's
They-
no y value there.
Yeah, they
at
must
those
be
numbers.
either a vertical asymptote or a hole. And in the last chapter, we figured that out. Actually, in chapter P, we figured that out. Because a hole is actually a removable discontinuity. So if we could remove the same factor, okay, then right here we have the same factor. Then this is where our what exists.
Hole.
Our hole.
So because the reason we factored the top and bottom was to look for factors that are the same. And by
Correct.
canceling the x minus 3's, we will have removed the discontinuity. So we will have a hole at x equals 3.
We will.
We'll talk about how to find the y value later when we start
We will.
graphing these.
Second.
And we'll worry about
day.
that later. But for right now, just a review. There's going to be a vertical asymptote. I always say that wrong. At x equals 5 halves. Good luck writing over there on the board.
See that?
It's horrendous.
Oh. Okay, ignore that. Pay no attention to the man behind the screen. Vertical asymptote at x equals 5.
Wish you could see
halves.
this. We're having to write like 6 inches above where it's showing up. So
It's a 5, and I'm
it's
not
a 5
fixing
halves.
it.
I'll fix it on the other one. But
Okay.
there's a vertical asymptote
Yep,
where that didn't cancel
Right
for
there.
that factor, but the factor that canceled is going to create a hole in our function of x equals 3.
okay.
All right, move along.
I think we're done with this example.
I'm done with that example.
Okay. All right, end behavior, Mr. Lecky.
In behavior is x squared over x,
It is.
and x squared over x simplifies to x.
It does.
And as x goes to infinity or negative infinity, this thing just grows like crazy. And we don't have a horizontal asymptote.
Asymptote.
I hate this word. We don't have ha unless the end behavior is a number.
Correct.
When the end behavior is infinity or negative infinity, the limit technically doesn't exist, and therefore the horizontal asymptote does not exist. And we have to look for a slanted, or if you want to be fancy, an oblique asymptote.
I'll even write down oblique.
Okay, and the way we're going to do this simply is division. If
Yay!
you remember our earlier example, we divided the numerator by the denominator, and the answer, the quotient, was a -4 plus a fraction as a remainder. The remainder went to 0, and our horizontal asymptote was simply -4. And while she's doing the division process,
Which you should be able to do.
this whole idea is the same. When you do the division, the quotient is where the function will be approaching as x goes to infinity, because the remainder will simply go to 0. 3 over x plus 1 will go to 0 as x goes to infinity, so the function will approach x plus 5. X plus 5 is a line. We call it a slanted asymptote that this graph for g of x will approach. All you have to remember is when you don't get a horizontal one,
Right?
division gives you
Long
the slanted
division.
one. You don't
Okay.
even need the remainder.
You don't. Not at all.
So if you screw up on the last line, it won't hurt you any.
That's okay. They do that too.
Yeah, well, it
Subtract
saves
them.
them some trouble.
Okay, so if I recall, for vertical asymptotes, we wanted to do some
Factor. You think they'll remember that?
I don't know.
Factor everything.
Factor.
Everything.
I think they'll remember they have to factor, but I think they might freak out and go, how do I factor?
All right. And the first thing we look for is holes that we can cancel out like factors so that we can remove them. And unfortunately, we have no holes.
No holes.
However, we do have one factor in the denominator of x plus 1. So x cannot equal what?
1, -1.
Negative
Sorry.
1, which means that is not going to be a hole because we can't cancel the numerator.
Correct.
So what is it?
So the vertical asymptote is not, x is not equal to 1. That's the value we left out of the domain. The vertical asymptote is x equals a -1. Remember, you got to write this like a line.
It's a vertical line. And the other one is a slanted line.
It
It's
is.
not x plus 5. It's y equals x plus 5.
Right.
So we have a va and a sa. And no ha.
No ha. Alrighty, I think that's it.